Hello, this is the last part of this course, and this is RT level design. Actually, what we have done so far is we have prepared you for getting into RT level design. We are not going to cover all the RT level design in this one lecture here, but all we're going to be doing is going to be showing you what's the procedure, and how do we go about RTL design, and then we show you an example for register transfer level design. Actually, what happens is there's a lot more to it than what I can cover here. There's a whole course. The next course is on RTL design, and then there we cover components, how to put the components together, the timing of it, which is based on the flip-flop timing, which you learned here. And then we get into far more complex designs, and then we get into not only one RTL design, but then interconnection of various RTL designs. So let's start with this, and in the time that we have, let's just get this subject introduced. Actually, we have done this already. We talked about the serial adder. Remember, the serial adder was a simple RTL design. Here we're going to be doing something a little bit more complex, a little bit more complete than that. The example we are doing is a multiplier, okay? And it is a sequential multiplier. So if you want to do a combinational multiplier, just like the adder, we have to add and add and add. So it's it's a two-dimensional array of adders, just like the adder itself. Which takes a lot of hardware. So what we're going to be doing is we're going to be doing a multiplier with less hardware, and that becomes a sequential multiplier. Sequential multiplier, the same way that the serial adder that we did uses one single bit for adding 8 bits. This uses one single adder, let's say a 16-bit adder, for multiplication of two 16-bit numbers. Okay, so that's the whole philosophy behind it. I can definitely add two 16-bit numbers with an array of 16-bit adders. I don't want to do this. I want to reuse one adder many times and then perform the multiplication. How do I reuse it? Well, I reuse it by using it once, storing the partial result, using it again, storing the partial result, and therefore I need registers, I need adders, I need controllers for controlling my multiplication process. That's why it becomes an RTL circuit. But then, at this stage, there is only so much I can do. Okay, I can do a multiplication by a very good shift and add algorithm that is usually done, or do a Booth algorithm multiplication, which is a signed number multiplication, which would require a lot less hardware than the combinational big multiplier, and also it requires fewer clock cycles. But then I don't want to do that first. What I want to do is I want to only show you a sequential circuit that performs multiplication. And then we talk about learning from it. We will do the complete design. We will do the Verilog. We will do the controller, and we will put the whole thing together. We will do the test bench. But then I say, well, this was our first design. This is not a good design. And then what do we do for a good design? Okay, let's do this. This is what I want to do. I have a start signal, I have a done signal. Let's only do 4 bits. Okay, and A bus and B bus contain my two inputs, and then once the start arrives, I collect A, I collect B, and then start the multiplication process. After multiplication is done, I issue the done signal, put the result on my final output bus. Okay, and my final output bus, let's say, is an 8-bit output bus. I have this standard clock and reset, which I'm not going to talk about. They are not part of the multiplication algorithm. They are not part of my hardware. They are part of my hardware, but they are not functionally things that I interact with. I respect them. I use them. I put them into the controller. I put them into the data path components, and that's it. So how do I go about this multiplication? See, this is what I can do. Just without thinking much, I say, I have a B and I have an A. Let's add B to itself a number of times. Okay, that's fine. Okay, what do I need for this? I need a register B. Okay, let's say a 4-bit register for B. And then I put A into a counter. Okay? And I keep decrementing the counter. Each time I decrement the counter, I add B to itself. But then I know that the result will be an 8-bit result because B is 4 bits, A is 4 bits. And therefore, I put B in an 8-bit register. As I'm decrementing A, I'm adding that 4-bit to itself, to itself, to itself. So I have an 8-bit adder. I have the partial result that keeps getting added to itself. And then I have the counter. So that's all there is to it. That is absolutely all there is to it. Why so simple? Well, there is no free lunch. It is simple. The algorithm is simple, but look, for a 4-bit multiplication, I can use up to 16 clock cycles. For a 64-bit multiplication, if my operands are 64 bits, I use 65,000 clock cycles for performing this multiplication. True, I save a lot of hardware as compared to the combinational multiplication, but then 65,000 clock cycles for a multiplication. Let's use the expensive combinational circuit because this is not the right way of doing it. But as our first RTL example, this is the perfect example. As our first RTL example, a dividing or a divider by subtracting B from A when you are dividing A by B, subtracting B from A until you can no longer subtract. That's a perfect algorithm. It's not good. It's takes a lot of clock cycles, but it gives you the sense of RTL design. So let's do this. The circuit sits and waits for a start. When the start is received, it collects A and B. When A and B are received, it starts counting and adding. When it's done, it will issue the done signal. It will keep the output on the result bus until the next operation begins. What do I need for this? Okay, without even going to the next bit. What do I need for this? I need a register for... what do I need for this? I am adding A to itself. Here, add A to itself B number of times. Okay, or I could do the opposite. I could do adding B to itself a number of times. All right. Inputs come in. I assume A bus is available. I assume B bus is available. Okay? A bus has A, B bus has B. I first load A into A register. Then I have an adder. The adder takes the A register and initially with 0, adds it to that register and puts it back into this register. The second time, the third time, the fourth time, as this is happening, a counter is counting the number of times that this add is happening. And then it compares it with the value of B. When the number of times I have added A to itself, B number of times is done, I'm done with my multiplication. And this is the data path for it. As simple as that. Okay? This is the very long description of it. And this is the multiplier data path. I have the A register that takes the A bus, puts it into the A register. I have the A register that is initially loaded upon reset is reset, and then when load A is issued, A bus goes into A reg. So this is the first register. Then I have that add register, the one that comes in after the add. And initially I load it to 0, make sure that it's reset to 0. And then from that point on, the add bus, which is the result of A and this register, will be clocked into this. Let's look at the add bus. Look at line 34. The add bus is A reg added with add reg. Okay, and this goes on the add bus. That add bus gets clocked into the add register. In addition, I have a counter here, and initially I initialize the counter to 0. But then from that point on, I keep incrementing the counter. And then I have a comparator. On line 33, I have a comparator that compares my B bus to the B counter. And when it's done, it issues a done signal. It issues a done signal to the controller, and the controller will be quitting after that. It says, well, that's good enough. No more counting, no more working. And then what it will be doing will be putting on line 35, it puts the contents of the address register, the add register on the result bus. That's the data path. And this is the controller. Look, I wait for a start. When the start is received, when the start is 1 and then back to 0, I do the loading of A. And then I wait in the counter state, wait until done is issued. When done is issued, I go to the idle state and I'm all done. Okay, I'm all done waiting for the next start signal. All right. So that's a simple design. That's not a very good design. This is the very long description of the controller. Remember we do the Hoffman model. This is the transition from idle to init to load to counter states. And this is the combinational part, issuing the next state. And then also issuing the control signals from the controller to the data path. Down here, I have the clocking. Again, positive edge of reset, positive edge of clock. Same clocking and reset as my data path registers. This becomes my controller. I put the controller and data path together. This is a test bench for it. This is a test bench for it, and then the test bench is applying data to A, to B, and issuing the start signal, and you're seeing that the multiplication results are shown here. 9 times 5 is 45, as shown here on the output bus. Okay, so it works. It works, but then again, it's not a good multiplier. It's a slow multiplier, okay? And if my, in here, for example, B is 9, it takes 9 clock cycles, Okay, it takes 9 clock cycles, actually this area, 9 clock cycles for the result to be ready. That's very slow. Okay, let me give you something. All right, let's do it differently now. Okay, the example I'm using is an 8-bit number or two 8-bit numbers. What I'm going to be doing is I'm going to add b to itself a number of times. Okay. What it means is, what is a here? 1, 2, 4, 8, 16, 32, 64, 128. So a is 148. A 1 0 0 1 0 1 0 0 has a 1 in position 2, has a 1 in position 4, has a 1 in position 7. Okay, that's why it made it 148. So if I want to do what I did before, what I have to do is to add b to itself 148 times. What it means is I have to use 148 clock cycles for performing this multiplication. But then I look at a differently. A has a series of ones and zeros. Okay? And let's say this is a number 0, 0, 0, 1, 0, 1, 0, 1. That's an 8-bit number. 1, 2, 4, 8, 16. 1, 2, 4. That's 21. Okay? Let's say in this position, this is a 1. It's contributing 4 to A. What it means is because of this 1, I have to add b to itself 4 times. I have to add b to itself 4 times. This, I have to add b to itself 16 times. This means I have to add b to itself 128 times. All of these give me 148 times. Instead of looking at the 148, let's look at the ones that form this 148. The one in position 2, which is add b to itself 4 times, instead of performing this, what if I just shift b 2 times to the left, 2 places to the left? What if I make b this 0, 0, 1, 0, 1, okay, 0, 1, 0. What is this now? This is 1 place to the left. This is, no, that's 2 places to the left, sorry. 2 places to the left is this. What is this now? Let's look. 1, 2, 4, 8, 16, 32, 64. This is 64, 70, 84. What is this? 21 times 4. So instead of adding 20 times to itself 4 number of times, I just shift 21 2 places to the left. Instead of, look at this 16 now. Instead of adding b to itself 16 number of times, I just take the resulting b. How many times? 4 places to the left. And then this one, 7 places to the left. And that's all there is to it. Okay? And each time I shift it, I will add it to the previous one. So this is B, for example, shifted 4 places to the left. I form another B, shifted, this is B shifted 2 places to the left. 2 to 2 is 4. Then I form another partial B, which is B times 16, which is B 4 places to the left. And then the next one, B 7 places to the left. I take all of these and add them together. That becomes my multiplication result. And therefore, what I do is I examine bits of A. Bit by bit, I look at 0. I say, no, I'm not going to add anything. I'm just going to shift to the left. Next one, same thing. Next one, oh, there is a 1 here. So let's add and shift. Therefore, this algorithm is called add and shift multiplication. I'm not going to go through any more details than what I have already shown, except that I'm going to be showing you the data path for this, and this works a lot faster than the previous one. Look, I have an A register, I have a B register, I have an A register. The A register, I look at the least significant bit of it each time I shift, so that I know the whether the rightmost bit is 0 or 1. As I look at that bit, I will be either adding B to the partial product or just shifting the partial product to the right. What it means is I look at A0. I look at A0. If A0 is 0, then I take my partial product, which is the B added to itself. Okay? The partial product, the B added to itself. If this is 0, I take B, 0 it out, and just shift P 1 place to the right. I don't add anything to it. If B is, if A0 is 1, then what I do is I take P, add B to it, and then shift it to the right and write it into P. Eventually, I have the P register and the A register become my result. This is a multiplication called add and shift. This is the data path. This is the data path. And this is the controller. I wait for a start. I load A and B, and then shift A, shift A, shift A, shift A, and at the same time load P. But then I will either select the, look at the AND gates here. I will either select the B register or select 0 to be added with the partial product. Okay, once again, the only reason I'm showing this to you is not to understand the details necessarily, but to understand that the way I showed you, the simple way that I went through the design of the data path of it and everything, that's not the right way of multiplying, but this is a good example for the last RT level design in class. Okay, so this is the controller, and what we have done is we have talked about a simple algorithm and also just a overview of shift and add multiplier. And this is actually where we begin in the next course with our RTL designs.